Hey everyone, ready to get our minds bent a little?
Always up for that.
I know I am. So today we are taking a deep dive into category theory.
Ooh, exciting.
I know. We're going to be basing it off of an excerpt from the Stanford Encyclopedia of Philosophy, really trying to explain some of the cooler parts of this super interesting but kind of dense topic.
It's a real brain twister, but once you grasp it, it's so elegant.
It really is. Okay, so the big idea with category theory, it seems like, at least from this excerpt, is kind of a shift in how we think about math.
Right, totally.
It's not so much about breaking down structures like we normally do, like what are the elements of a set or all the pieces of a group. It's kind of zooming out and
Exactly.
looking at the bigger picture.
It's all about relationships.
Okay, so less about what things are and more about how they relate to each other.
Precisely.
So how does that actually work in practice? I mean, how do we go from thinking about sets and groups and all that to thinking about the relationships between them?
Well, think about it this way. You have sets, topological spaces, groups, all these different mathematical structures that seem totally different. Category theory says, hold on, let's not get bogged down in their internal details. Let's see how they connect, how they talk to each other.
So what's the language they're speaking? How are they talking to each other?
It's the language of morphisms, these special maps that preserve structure.
Morphisms. Okay, so I guess like a function between sets would be a morphism?
Exactly. A function maps elements from one set to another, but it also respects the set structure, right? And you have continuous functions between topological spaces. They preserve the topological structure.
So they're kind of like translators helping us understand how different structures relate.
You got it. Morphisms reveal the hidden connections across all these different areas of math.
Okay, that's cool. So we're talking about these relationships, these morphisms. The source also mentions universal properties, and I have to admit that sounds a little intimidating.
It can be, yeah.
Can you break it down for us? Like, how do universal properties fit into this whole picture of relationships and connections?
Well, imagine you're trying to define what a product is in mathematics. Traditionally, you might list out its elements or describe its internal structure.
Right.
Category theory says, no, 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 let's define it by how other objects relate to it.
Okay. Interesting. So instead of saying what it is, we're saying how it's connected.
Exactly. It's all about relationships. A categorical product, for instance, is defined by how other objects map into it uniquely.
So it's like saying this product is special because it's the most efficient way to connect these other objects.
You got it.
Mind-blowing. So category theory is about finding these elegant patterns, these universal properties that define things by their connections.
And we've only scratched the surface. Wait till we get to functors.
Oh yeah, the source mentioned functors. They're kind of like translators, but between categories. So we're going meta now, translating between different translations.
You got it. A functor takes an idea from one category and expresses it in the language of another.
Okay, so can you give me an example? Like a concrete example. I'm having a little trouble picturing what these functors actually do.
Okay, let's think about homology from algebraic topology. It connects topological spaces, so think shaped surfaces. It connects those to groups, which are sets with a special operation.
Okay, so we're bridging geometry and algebra. But how does a functor do that?
Well, homology assigns to each topological space a bunch of groups. These groups capture information about holes in the space.
Holes. Okay, I'm intrigued.
And here's the key, a continuous map between spaces. Remember, that's a morphism in the category of topological spaces that gets translated into a homomorphism between the corresponding homology groups.
So the functor isn't just translating objects, it's translating the relationships between them too.
Precisely. It's preserving the structure of the relationship as it translates from one category to another.
That is pretty wild. It seems like category theory is revealing these connections between areas of math that I never would have thought of as being connective.
It's pretty amazing, right?
Yeah. Can you give me another example?
Sure. Even something as familiar as taking subsets. That's a functor too. The power set operation, it takes a set and sends it to its power set, and it also translates functions between sets into functions between their power sets.
So even something basic like taking subsets fits into this framework.
Yep.
I'm starting to see how powerful this perspective could be.
And it gets even more powerful when we talk about maps between the functors themselves. Those are called natural transformations, and they take us to a whole other level of abstraction.
Maps between maps. Okay, I think my brain needs a break.
Haha, I know what you mean.
We're going to have to save natural transformations for part 2 of this deep dive, I think.
I can't wait.
All right, so we're back, and I'm still kind of reeling from all this funker talk.
It's a lot to take in.
I know, right? Like translating between categories, preserving those relationships. Pretty wild.
It is, but it gets even wilder when we start talking about natural transformations, these maps between functors.
Okay, hold on. Before we get to that, can we go back to the power set example for a second?
Sure.
You said it's a functor, but I'm having trouble seeing how it's actually translating anything.
Right. Well, remember, a functor has to do two things, map objects and map morphisms.
Right.
So for the power set functor, it takes a set and sends it to its power set that's mapping the objects.
Okay.
But now let's say you have a function between two sets A and B. The power set functor has to translate this function into a function between the power sets of A and B.
So how does it do that?
Well, it uses the original function to create a new function that sends each subset of A to its image in B. Basically, you're applying the original function to all the elements of the subset.
Ah, okay. So it's like the funker is lifting the original function up to the level of subsets.
Exactly. It's preserving the way elements are mapped, but at a higher level.
Okay, that makes sense.
And this idea of lifting operations to higher levels of abstraction, it's a big theme in category theory.
Interesting. Okay, so we have funkers that translate between categories, but then you said natural transformations are maps between funkers. Why do we need those? What do they add to the picture?
Well, think about it this way. What if you have two different functors that both go from the same source category to the same target category? Natural transformations give us a way to compare these functors to see how they relate to each other.
So it's like we can say these two translators are kind of similar, but they have slightly different approaches.
Yeah, it's a great way to think about it. A natural transformation gives us a way to map the results of one funker to the results of another, and it does it consistently across all the objects in the source category.
I think I'm starting to get the concept, but can you give me like a visual, a concrete example?
Sure, let's look at vector spaces. There's a funker that takes a vector space and maps it to its dual space. The dual space is the space of all linear functionals on that vector space.
Okay.
And then there's another funker that takes a vector space and just sends it to itself, the identity funker.
So one is mapping to the dual space, and the other one is basically doing nothing.
Right? Now, there's a very important natural transformation between these two functors. It takes a vector in the vector space and maps it to the linear functional that evaluates other vectors on that vector.
Okay, so this natural transformation is connecting the original vector space to its dual space.
Exactly, and it highlights this duality between a vector space and its dual space, which is a super important idea in many areas of math and physics.
Wow. So natural transformations are like bridges between funkers, connecting their outputs in a meaningful way.
They are.
This is so abstract, but I'm starting to see how powerful it is. Like we're seeing these connections that weren't obvious before.
That's the beauty of category theory. It reveals these hidden connections and patterns.
It does. Okay, so we've talked about funkers' natural transformations. The source also mentions these things called adjoint funkers, and they sound really interesting.
They are super interesting.
It says they're like finding the best possible solution to a translation problem.
That's a good way to think about it.
Can you explain what that means? Like, what are adjoint funkers, and how do they give us the best possible solutions?
Okay, let's start with a classic example, the forgetful functor. It takes a group and forgets the group structure, just gives you back the underlying set.
So it's like stripping away the extra information.
Right. Now, the adjoint of this forgetful functor is called the free group construction. It takes a set and creates the most general group you can build from that set.
Okay, so we forget the group structure, then try to rebuild it. What's so special about that?
Well, the key is that the free group construction doesn't give you back the exact same group you started with. It gives you the closest possible group you can build from that set while still obeying the rules of being a group.
So it's the best fit group for that set.
Exactly.
Cool.
And this pattern of forgetting and freely reconstructing, it pops up everywhere in math.
Really?
Yeah, we see it with abelian groups, topological spaces, even in really complicated stuff like the Stonecheck compactification.
Wow, so many different ideas all fitting into this one framework.
That's the power of category theory. It unifies all these seemingly disparate concepts.
It's incredible.
It is. And this idea of the joint functors, it goes even deeper. There are these special morphisms called the unit and the countit that really capture this notion of best possible solution.
Okay, I'm intrigued. Tell me more about these unit and countit things.
All right, let's stick with our forgetful funker and free group example. The unit of this adjunction is like a bridge. It takes you from a set to the free group on that set.
So it's taking the set and embedding it into this richer structure.
Exactly. And the special thing about the unit is that any way you choose to map that set into any group can be uniquely extended to a homomorphism from the free group to that group.
So it's like the free group is generous enough to include any possible mapping from the set.
Yes. And the countit goes in the opposite direction. It takes a group and sends it to the group you get by forgetting the group structure and then freely constructing a group from the underlying set.
So we forget and then remember the group structure as best as we can.
You got it. And the special thing about the countit is that any homomorphism from a free group to our group can be uniquely factored through this forget and reconstruct map.
So the unit ensures we're including everything, and the countit makes sure we stay as close to the original group as possible.
Exactly. They work together to make this adjunction the best possible solution to the problem of forgetting and reconstructing the group structure.
This is blowing my mind.
I know, right? Adjoint functors are one of the most powerful concepts in category theory.
They are. Now, the source also mentions this other thing called topos theory.
Ah, yes, topos theory.
What are toposes and why are they important?
Topos theory is where category theory gets really philosophical. A topos is a special kind of category that's rich enough to do a lot of what we usually do in set theory, but with a twist. It is a twist. Toposes often use a different kind of logic, intuitionistic logic.
Intuitionistic logic. Okay, and what's that?
It's a more constructive logic. You can't just prove something exists by showing that its non-existence would lead to a contradiction. You actually have to show how to construct the thing.
Interesting. So it's like a more hands-on approach to logic.
Yeah, exactly.
So by working within a topos, we're kind of doing math with different rules.
That's a great way to put it, and it leads to some really interesting results. For example, in some toposes, the statement, every function from the real numbers to itself has a fixed point, that statement is actually false.
Wait, really? But isn't that like a fundamental theorem?
It is in classical analysis, but in intuitionistic logic and in these particular toposes, you need additional assumptions to prove it.
So topo theory is challenging our assumptions about what's true in math.
It is. It makes you question what mathematical truth really means.
Wow. This is pretty mind-blowing stuff. It's like we're exploring different mathematical universes with different laws of logic.
That's a great analogy.
I want to learn more about topo theory, but I have a feeling this is just the tip of the iceberg.
Oh yeah, we've barely scratched the surface. There's so much more to category theory limits, colimits, monads, sheaves. It's a huge field.
It sounds like it. Well, I think we're going to have to wrap up our deep dive into category theory here, but wow, what a journey.
It has been a wild ride.
I know. From Morshisms and functors to natural transformations and adjoint functors, it's been a lot to take in.
But hopefully our listeners are as fascinated by this stuff as we are.
I hope so too. Category theory offers such a powerful way to think about math, emphasizing connections, relationships, and finding these elegant abstractions that unify so many different ideas.
It's truly a beautiful subject.
It is, and I encourage everyone to explore it further. You never know what incredible insights you might discover.
Absolutely. Happy exploring.
And that's it for this deep dive into category theory. We'll be back soon with another mind-bending topic, so stay tuned.